All right. So let's go into it. So we have flat plate heat exchangers. We went over these in the last freshwater generation. All right. They carry hot fluid on one side of the plate, and on the exact other side of the plate is going to be cold fluid, and they're stacked up. All right. And you have that heat transfer between plates. All right. The plates are the ones that are separating it, but in between them is what's flowing. Your cool fluid on one side. I'm going to redraw these. And then you have your hot fluid on the other. All right. All those plates are doing is just separating this fluid. All right. Now, breezing over that because we've already seen that in the last slide. All right. The plate type distiller. All right. These things were designed to be used with a diesel engine as its source of heat. That was their primary design. And they would basically be circulating jacket water, and jacket water is, it's just, it's like radiator fluid in your car. All right. It's treated water. It's going to be circulating inside of your main engine for your diesel engines, and they go off to some sort of a heat exchanger to be cooled down, and then they're brought back into the engine. All right, so that's just jacket water. So our feed pump is still our feed pump. It's still bringing in salt water. All right, and this is our plate type distiller. So what we're utilizing is the heat that we're going to be generating from our main engine to boil the water in our evaporator to create distilled water. All right. So we have our feed pump. It's still producing salt water. Well, it's not producing. It's still pumping out salt water. It's going to be preheated in a condenser while also getting fresh water to be produced. Then some of it goes into the evaporator. A lot of it goes just overboard. And it utilizes an air ejector and a brine eductor. So they're both utilizing the Venturi effect. All right, so whatever is going overboard, all of your salt water that's going overboard is going to be drawing a vacuum, and it's also going to be sucking out any of the brine. All right, so it's going to be two different ejectors. So we do not have a diesel engine that's going to be running long enough on the TSES. So we utilize a glycol system. All right. So we have glycol that circulates in and out of the plate type distiller instead of jacket water. And we use steam, our auxiliary steam, to heat up the glycol. All right. And this is our Nyrex on board the ship. I can tell you firsthand, these things are great. They produce a huge amount of water. They're not finicky. It's, those flash type evaps and those submerged tube type evaps take weekly maintenance if you're running those things rough. You're going to have to basically every week you get in the habit of having to take those those submerged tube or flash type evap. Every week you would have to do an acid treatment on it, and you're basically trying to clean these things with acid so that way you get the best heat transfer as possible. And if you don't do that, you basically get this scale, which is like this fast acting like hard water that builds up on all of the tube bundles. And it gets to the point where it'll actually start to crack some of the copper tube bundles. And then you have leakage of the steam or the jacket water, whatever you're using to heat up the salt water, and you just have more problems. These things, I've had it run for 3 months straight and I've had no problems with it. The only problem I had is this fresh water pump went out. That was because of a bearing. But this thing was literally maintenance free for 3 months. A little bit of water treatment that you had to put in. But they're great. And they're great for that reason is the level of, like I said, maintenance just goes way down. All right. So you still have your evaporator, all right? You still have your condenser, but everything is just pretty much vertical on itself instead of being separated into two different vessels or systems, all right? So this is the plans of what it is on the TSES. All right, here's your chemical treatment. This is what I was talking about that you would have to add in onto the line. It's almost like a half and 55-gallon drum. You fill it up like once a week. It's not the worst thing in the world. And this is basically the path that it takes. So you have your saltwater path. All right, it's going through a plate type heat exchanger up here. Then it goes down, and half of it is going overboard. It's this air brine ejector. And then a small amount is going into the actual evaporator. All right. And this is what's happening here. You see you have it going around the plate type heater. It's not just like the plate type heater is submerged in it. It's not like it's a submerged tube type plate heater. All right. It's still following the same principles. And then over here, we have a demister. This is to basically separate, as we've talked about many times, if you have any entrapped water molecules or any minerals that are entrapped into the vapor, that will separate it. All right. And then what you have up here is just pure vapor. All right. Any questions on this before? Okay. So again, this is just another view of what's going on. This is your saltwater cycle. This is your distillate that's coming out. All right, all your vapor comes up, goes out, goes to a freshwater distillate pump. You have your salinity cell, and you have your solenoid dump valve. All right, and then you have a production meter. Again, your numbers are very important on vessels of what you're producing, what you're using. The vessel that I was talking about that I had a problem with my freshwater pump, where it actually caught fire because of the bearing, the number of production meters were very important at that point, because we would have run out of water a week ahead of time if we didn't start shutting down laundry every other day. So we still had like 2 weeks left at sea, and we only had like 4 days left of water. And this was all due to a calculation that I did, all due to our production meter and how much we were using a day in our averages. All right, we were able to spread that out from 4 days down almost to like a week and a couple days, just by shutting down laundry and telling everyone to be really, really careful, otherwise we would run out of water. And are also, because of everything that was going on with that, we were able to come into port with a couple days left to spare. All right. So production meters and numbers on vessels are really good to have. So things like that happen, you'll be able to predict how far out you are or how drastic of a measure you would have to take. All right. Because the next step after shutting down laundry every other day would be to shut down laundry altogether. And then after that, it would be, you would have shower hours. So you would only be able to shower at a certain time of the day.
So in dock all over again.
Well, it's not like in dock. It's just like what you have to do to make sure you still have enough water to, make food. And you would have like 5-minute showers, like those sea showers they talked to you about, where you basically rinse your body, sud up, and then rinse it all off. That's kind of what you had to start doing. Didn't think I would ever need that again, but there it was. And of course, this is our heating cycle. All right. Same thing again. Salt water was circulating on one side of it. Where is the pen? Come on. You have the salt water circling down here. And then you have your heating cycle going on the opposite side of it. All right. This is old pictures of them. Now it's the globe that's down in the engine room, as I'm sure you're all aware and have seen. This is what the inside of them look like. You have plates basically just right there. All right. Now that's that moisture separation screen that was talked about. Any of that vapor that I said that would have any entrapped liquids or any like minerals that are entrapped into the vapor that's getting brought up because of the energy will basically get trapped here and fall out. All right. Now, the one on board the TSES was basically a prototype. They wanted to see it in action on board of like a vessel, not just like in a lab or whatever. And they've gotten a lot smaller since then. All right. They produce a huge amount of water, like we've talked about. They're very nice because of you can concentrate on other things. I still really like flash type EVAPs because I just think they're super cool. And they don't use tube bundles. But these things are nice because, like I said, they're almost maintenance free. And when you come into port, you shut down, you do a nice big acid bath onto these plates, and it's all happy again. All right, now you have these things called vapor compression distillers. All right, so we have a saltwater feed. We have an electric heater that's used on startup. The electric heater is heating up the water. We end up with 2 PSIG, all right, 219 degrees vapor, which means what? What's happening inside of that? Is it in a high pressure state? What's 2 PSIG mean? Where are we compared to atmosphere?
Above.
Say again?
Is that 1 above?
It would be 2 above. Remember, PSIG 0 point is what we're in right now.
Oh.
Okay. So we're in a high pressure state. It's 2 PSIG. Doesn't seem like it's a high pressure, but it's above atmospheric. With distillers, like we talked about, it all comes down to your atmospheric state. All right, 1 atmosphere is your reference point. So we use this vapor, and it goes into a compressor. Does everybody recognize that as some sort of like a low pump? constant volume pump, positive displacement. So that compressed vapor is at 3.2 psig. It's increased its temperature because of the work we're adding with our compressor. That goes into a tube bundle. All right. We turn off our electric heater because now no longer do we need an external heat source. All right. Again, it's not like we're just making energy out of nothing. We are adding work in the state of our compressor. Okay. And as we go through, we are heating up our salt water. And then as it exits, it's like in its 50% vapor, 50% liquid state. And then as it goes through, it's doing that whole preheating and it's cooling itself off. And now it's fresh water on the side. And again, you know, constant theme here, this delta T that we keep bringing up, you know, which is the temperature of the high versus minus the temperature of the low. Right here is relatively a super hot temperature, 223 degrees. That salt water is at like 50 degrees or something like that, right? So in order to turn this back into a liquid, and a full liquid at that, you're going to have the greatest delta T if you're constantly doing that reverse flow, which we're still having. All right. Your largest delta T, of course, would be here, would be at this point to this point. But to create an even large scale delta T that we're having is that you would do that reverse flow, which we're having here. And who can forget about brine? It still goes overboard. All right. I haven't seen this except in this class. All right. You're going to basically see, you know, submerged tube, flash evaps, and Nirexes. That's really what you're going to see out there. You know, I worked on OSVs. We didn't even have water making capabilities. We had such a, you know, we were basically a tanker that we would just gain so much water that we'd be able to be out there for a couple months, no problems. Because there was 13 people on board and we had no issues with, you know, cooking, showers, nothing. We were never on water rations. We just had these giant tanks that we would fill up. But, you know, most of the time you will be on a vessel that will be creating water. All right. And last but not least, you're going to be seeing these reverse osmosis machines. All right. So with osmosis, you have a semi-permeable membrane. And usually what you're going to be seeing is that the dilute's going to be going into the concentrate. That's normal, natural, what would happen if you just left this alone. So in order to force it to go the other way, we have to, because we have concentrate, this is our salt water. We want it to go this way. We need to produce osmosis pressure in reverse. All right. So this is what they basically look like. They can come in like these cartridges. They basically look like filters almost, but they have more of, they look and feel more like fiberglass if you actually get to look at them. They kind of look like a mixture between like an oil filter and a filter you would put in your household air conditioning unit, something along those lines with a little bit more of an element of a fiber. Like we talked about before, we have these high pressure pumps with a motor. So we're producing work. We're using work from an external source to add into it. And that pressure that we're going to put into it is going to reverse the flow of nature. And we're going to get a dilute. And this is what we're going to be getting out of it. We're going to be getting fresh water out of salt water just by filtering it. All right, but what stays behind is all of the minerals, all of the, all of the salts, everything like that. And again, of course, you can't forget about brine. And like all filters, you have your everything that's nasty on the outside, everything that's good from it is on the inside. So a typical two-stage, and a two-stage is requiring to the pumps, all right, and also to the filters themselves. All right, each one of these are not going through. It's not like it goes through one filter and then comes out and goes through the next filter. It's not going through 6 filters. It's going through only 2 filters. All right, so salt water goes into each one of these filters. They come out at 200 ppm. They get repressurized, and they go into another set of filters. All right, everything that's left out of this level of filtration here, out of your 5 ppm filters, is going to be recirculated back into it. All right. So you have these pre-filters, and this is a pre-filter so that way you're not clogging up these reverse osmosis filters, because these reverse osmosis filters typically, depending on the manufacturer, can only be cleaned once. And you only get about half life cycle after cleaning it. It's not like it's that great. I've tried cleaning them. It's super annoying. You'd rather just buy a brand new one, because you do a huge amount of work for really no results. Depending on how long these filters, the environment that you're in, these filters can last, months. They can last weeks. It all depends on what type of environment you're at. And the filter that we were using on this boat, our environment was not great. We were on a dredging vessel, and so had a huge amount of sand slurry that was all around the vessel at all times. So when you tried pumping in salt water in order to filter it down to 5 to 20 ppm, you remember, we're not trying to flash this stuff. We were trying to filter it down. And you can imagine how quick these things clogged up, even if we had a pre-filter. So sand just clogged this thing like crazy. So we were changing these things out weekly if we kept this thing running. So because we haven't done any boiling or any high heating, these things aren't sanitary at this point. The water's coming out of here is pure, but we still have to do a UV treatment, all right, in order to kill anything in it, and a charcoal filter just in case anything has gotten through, all right. These are commercial first stage, and we've talked about these media filters before in the spring semester, but these media filters are basically like they're small down pool filters. All right. What they utilize is sand. All right. And you have your water coming in on top, and all of the contaminants just kind of settle inside of the sand, and the sand is a natural filter as it goes through. All right. So what we have here is a sea strainer first. That sea strainer is going to take care of any of the big stuff, seaweed, crabs, anything you can imagine, because this pump is going to suck in whatever it wants. It goes through a booster pump, and then it goes through a media filter. These media filters can be back flushed. They can be cleaned out easily. They're just sand inside of there, or some sort of sand-like element. And as they come through, they go through a pre-filter. They go through an oil water separator. That's just in case you get any oil that's going into it. All right. Then you go into a high pressure pump, and we go into a RO. your actual reverse osmosis membranes. And this is a one stage, it's a singular stage. So it's just going into one filter that'll go from 5, where we're at, to 500 ppm. And then it'll go down to 5 ppm on the other side. You have your normal salinity probe. And as we come through, we look at what we have. This is our brine discharge. We go through our charcoal filter, UV sterilizer. So it's just blasting with UV, and it goes into our potable water. All right. That's how this system just basically works in a nutshell. These things come in units. All right. You basically buy them as is. It's not like you can build these things, out of scrap parts that you have in the warehouse or whatever. They're basically, you buy them as a set. All right. Now let's just talk about freshwater storage, potable water storage all over the TSES. We have our engine room. All right. We have our distillate tanks. So we have 3 distillate tanks in the engine room. We have our starboard inboard, we have our port inboard, and we have a port outboard. All right. There was a tank here probably at one point. It's been removed. Okay. We have our forward peak, or just known as forepeak. All right. And then we have aft peak. So grand total of distillate that we have is 1, 2, 3, 4, 5. 5 distillate tanks. All right. We will almost always suck only from the tanks that are inside of the engine room. So why would we have 109, 105 tons of distillate if we're just going to be barely going through about 75 tons? Why would we need an extra 200 tons? It's not our drinking water, so it's not like we're going to be, drinking this. It's all going to our boilers. Who has an idea? There we go. So, Chad's saying in case of an emergency. So what type of an emergency would we have that we would need 200 tons of salt water where 75 tons wouldn't be able to handle it? If our freshwater generation failed, yep, that would be one. This happened like the year before I went to the school. They salted the boilers. So those flash evaps that exist on the port side of the engine room, main engine room level, like right here. We don't use those anymore to produce our distillate. But someone tried to start it up and see if they can get them going. And they successfully got it going. But what they were producing was not distillate. And so they put a huge amount of salt water into the boiler. And what they had to do is they basically had to flush the boiler continuously. And they were just using all of this water in both these tanks to just push and try and remove as much of that salt water that goes into the boiler. Remember, like I've talked about it in those flash evaps and the submerged tube type evaps. The reason that they're not great because of maintenance is, like I said, you have to do these acid baths, and what you get on the outside of it is the scale, and the scale builds up like crazy. And if you're not careful, you know, one, it insulates. So it doesn't give you a good, it's not a good, you know, it doesn't give you good heat transfer properties. All right. So now you're trying to throw more energy at it to get the same result. You know, it also will, because these two bundles are so close to each other, they'll constantly build up, and the other side will building up on the other side of it, and they'll crack the two bundles. So imagine that whole thing is happening on the outside of those two bundles in the flash evap. But what about a boiler? We're sending salt water into a boiler, and our water is not flowing on the outside of these two bundles. It's on the inside. So imagine a scale deposit showing up on these inside of these tubes. And these tubes aren't that big. You know, they're about that big in diameter. All right. So imagine that scale going on there. It's high pressure. You know, we can't just change out our tube bundle like we would on a flash evap. You know, it's can cause some serious damage and some serious problems, considering that's where you make your electricity, that's how you make your fresh water. You know, all of these things just keep coming, you know, from our boilers. When we talk about it, look how much we talk about how, you know, we don't use main engines. We're not using jacket water to heat something. We're using steam because we have an excess of it. You know, we're using steam everywhere on board the vessel, and how much of a problem is if you take that ability away from yourself. All right. And finally, let's talk about our potable water. All right. So we have 3 tanks: starboard, port, and center. Who knows why center is so low compared to starboard and port? How do you get into AMS from the engine room? You go through that AMS tunnel, right? So that's the actual reason why that center is at a lower amount. All right. So, any questions regarding freshwater generation? Are you guys good? All right. So today was a quick class. One question for you guys. Have you guys actually seen what you're working in order to get to? Like, have you guys seen a Merchant Mariner credential? Your MMC? Okay. So these are what they look like. All right. This is my thirds. This is my seconds that I just got in the mail the other day, because this one just expired. All right. They basically look like a passport. You know, nice little Coast Guard information in it. Now, this is what you're fighting for, is this little piece of information in there. As it focuses, that little third assistant engineer. All right. So I just give you guys an idea of what it looks like, because I actually had no idea until I got mine. But this is everything that you're looking to get. All of these certifications, you know, that's going to allow you to go work out there or get a job in, you know, a hospital, and shows that You can work on a ship, so you can work in power plants and hospitals and everything else like that. All right. Any questions? Nope. You guys good? All right. Like I said, pretty short class today. I will see you guys all on Monday for a quiz. I have one, but it doesn't have the third officer word in it yet. So the center take for the potable water, why it's only at 261 tons? There you have the AMS tunnel. All right, that tunnel is what's that tunnel takes up a good amount of space as you go through those potable water tanks. All right, so that's why that tank is so much smaller. Okay. That's just to keep you, that's not going to be something I'm going to be quizzing you on or testing you on with that. But it's just something to keep you aware. As you're going around in a ship, you should constantly be aware of what you're surrounded by and what reasons are going on. What's going to happen on the other side of a wall in an engine room is very important. It's important in fires. It's important if you're going to be welding on that wall, you need to know what's on the other side of it. If you're going to be tooling on it, there's so much that goes on that just to your awareness. You're in a finite space. Get to know it. If you see ocean, you've gone too far. You guys should know your ship by the back of your hand. And it's not just the TSES, that just goes for life when you go through. All right, but start with the TSES. All right. Let's see. Other than that, guys, like I said, Quiz Monday, that's going to be on Freshwater Generation 2. Then we have Exam 2 next Thursday. All right. Keep up the good work with what you guys did with Exam 1. So you guys will be all right if you just keep up this pace. See you all Tuesday.
Have a good one, Professor.
Have a good one. If you have any questions, I'll stick around if you guys want to talk about grades or this or that or anything. You guys need anything?